right, folks, that was a great lesson in home automation. And next we have the founder of BDTi and also of the Embedded Vision Alliance, which is running an event co-located with us next door. The big event will be tomorrow, so you're all invited if you pay the ticket. And his name, please welcome Jeff Bier.
Thanks. Thanks, Ori, and thanks for hosting the Embedded Vision Alliance here at AWE. It's been a great collaboration. My name is Jeff Bier. I'm founder of the Embedded Vision Alliance. I'll tell you a little bit about the organization at the end of my talk, but what I want to talk about now is vision, starting with human vision. Neuroscience tells us that approximately half the human brain is devoted to vision. I take two inferences from this. One, vision must be important to humans because evolution tends to be efficient in allocating resources, and to justify allocating half of our brains to vision, we must get a lot of value out of vision. And of course, we don't need neuroscience to confirm this. Just try getting through your day with your eyes shut, and you'll very quickly realize just how extensively we rely on vision to enable us to do so many things. The second inference is that vision must require a lot of computation, because the human brain is an extremely powerful computer. If it takes half of that extremely powerful computer to process vision, that's a lot of processing power. These inferences from neuroscience align very well with our experience with artificial vision, typically called computer vision, or in our preferred terminology, embedded vision. In other words, when we enable machines to see, we give them really powerful capabilities, analogous to what humans gain through vision. And enabling machines to see requires enormous computation power. So this is what I want to talk to you about today, is how we're enabling machines to see and why there's a sudden proliferation of machines that see. What is driving that, and what is enabling it, and what are some of the implications of it? Very much building on the previous presentation, I think that most of you would probably agree that most of our technology is useful only to the extent that it interacts with the physical world in some way. I love shopping on Amazon because with a few clicks of a mouse, I can figure out which product I want and make it magically appear on my doorstep 48 hours later, the physical world. I love using my microwave oven because very quickly and easily, with the press of a button, I can prepare delicious food, the physical world. So if you agree that machines are primarily useful to the extent to which they interact with the physical world, then I would contend that the interaction of machines with the physical world through visual inputs to those machines is the most powerful way for those machines to gain information about the physical world. They can gain the most information, and the most information per unit time about the physical world through visual inputs, much as when I look out at this room, I can take in an enormous amount of information at a glance. If I try to transcribe that information in a textual description, it would take me hours, and it would still be very incomplete compared to the visual representation. So by enabling machines to see, we enable them to know more about their environment. And when they know more about their environments, machines can be smarter. They can be more responsive. They can be safer. They can be more efficient. They can be more capable. That's what's compelling about giving machines the ability to see. And of course, vision is an essential enabling technology for augmented reality. Augmented reality systems rely on vision for the system to orient itself relative to the physical world, to identify specific objects in the physical world, and then overlay additional information in a way that's coherent with the physical world. How's that? Better? Yeah. Okay. I think somebody's Internet of Things is jamming me. Don't tell them about our master plan to dominate the universe by gaining sight. Giving machines the ability to see enables them to know more about the environment. When they know more about the environment, they can do more for us. Computer vision is the term that's traditionally been used to describe this idea of extracting meaning from visual inputs through technology, through algorithms running typically in software on programmable processors. That's a technology that's been around for 5 or 6 decades. And for almost that entire history, it's been an expensive, exotic, niche technology deployed only in a few places, like high-tech manufacturing, Mars landers, exotic weapons systems, and so on. That's changing now very, very fast in a very big way. And we use the term embedded vision to denote this transition from the exotic, expensive computer vision technology to the ubiquitous, efficient, practical, embedded vision technology. It's a difference between a vision system that fits in the cargo area of an SUV, like you might have in the DARPA Grand Challenge, racks of gear, kilowatts of power, cubic meter of volume, to a vision system that can fit in your pocket, in a smartphone or a smart pen. What's enabling this transition and why it's happening now, as opposed to 5 years ago or 5 years in the future, is primarily improvements in the enabling hardware, the semiconductors. Going back to that inference from the neuroscience, that it takes an enormous amount of processing power to perform vision, and I'll talk in a minute about why that is. This makes it a real challenge to deploy vision widely. If you need 10 or 100 billion operations per second of compute power, which is typical for vision applications, or even more, I think I was jamming myself. If you need 100 billion operations per second of compute power and you need it to fit in your pocket, cost $100, and last a week on a battery charge, that's the real challenge. And that's what we have not been able to do until now. It's really tough to get that much compute power in a really small, low-cost, low-power package. Now we can do that. We're going to hear from Simon Morris at CogniView later in this session. That's exactly what his company does, is deliver those kinds of processors. It's not just the processors. There are analogous improvements in sensors and associated improvements in algorithms, software development tools, and so on. But I would argue that the processors are the most critical thing that have crossed a threshold now that's enabling us to put sophisticated visual intelligence into almost any product. What that enables is incredible. There are hundreds, if not thousands, of products reaching the market now, about to reach the market, that are possible only through visual intelligence. I wish I had an hour to go through and show you and talk to you about many of these really compelling examples in all kinds of different markets. I don't, so I'm going to just show you one that I think is one of the most compelling. This is a visual aid for people who are visually impaired from an Israeli company called Orcam. Can we have the audio on the laptop, please?
I want to show you today how this device changed my life.
She's nearly blind.
Maverick.
Great, let's go there.
Red light. Green light. $50 shekel.
50 shekel. Let's buy some coffee.
Breakfast. Bagel plus coffee with cream cheese.
So you can see there's a small camera attached to the earpiece of her eyeglasses, also an earphone, and in her pocket a device about the size of a smartphone that takes the image from the camera, uses the location of her finger in the camera's field of view to determine a focus. What is it that we're interested in here? And then gives her an audible interpretation. Oh, that's a 50 shekel note, not a 10 shekel note. This is Masrick Street. That's a don't walk sign. Oh, wait, it just changed to a walk sign. Really, I think, compelling example of embedded vision and of augmented reality, although a slightly different mode of augmented reality than what we're used to seeing, possible only because we have now the ability to deliver hundreds of billions of operations per second of compute power in something that fits in a pocket and runs all day on a battery charge. Plus, of course, the very small camera, the associated algorithms and software development tools. Now, I've said that these problems are hard computationally. They require many billions of operations per second. Why is that? It's fundamentally because of the infinite variety of scenes that appear in front of an image sensor. With all their detail and all of their potentially confusing ambiguity, like objects of interest being partially obscured by other objects, or in some cases maybe temporarily completely obscured. A confusing orientation, like trying to recognize a person's face when viewing them from a very difficult angle above. So many factors affect what we see in a visual scene and create lots of ambiguity. The human brain's very good at resolving that ambiguity, so we think we know what we're seeing, but optical illusions show us that actually our brain is filling in a lot that isn't really there. It's helping us make coherent sense out of a scene that's actually very chaotic and confusing. For vision systems, making coherent sense out of that confusing input requires very sophisticated algorithms. And when we have very sophisticated algorithms operating on lots of data, and image data, video data is lots of data, millions of pixels per frame, typically 30 frames per second, higher in some applications, hundreds of millions of pixels per second being processed by very complex multi-layered algorithms. That's why we need tens, hundreds of billions of operations per second of compute power or more to make sense of these scenes. Further complicated by difficult lighting conditions, weather conditions, and so on. Glare, shadows, bright light here in this part of the scene, dark shadows in another, make it very complex to get systems that reliably extract meaning from visual inputs. So that's why we require a lot of compute power. Getting a lot of compute power in a small, low-cost, low-power package typically means using specialized processors with lots of parallel compute capabilities. We're very fortunate that those processors are now becoming available to enable us to build these kinds of products, but it's also significantly more complex to program those kinds of processors than the kinds of general-purpose CPUs that power our mobile devices and PCs and so forth. So that's an additional challenge. There's also the very practical challenge that very few people have experience building vision systems because it's been a prohibitively expensive technology for most markets. So of the population of people who could now be putting visual capabilities into products, 99.9% of them have no prior experience doing that. And that's a real challenge because they're complex systems requiring complex algorithms, sophisticated programming techniques, specialized processors, a knowledge of sensor types and trade-offs, and so on. And so this is what motivated us to form the Embedded Vision Alliance. The Embedded Vision Alliance is an industry partnership made up of about 40 technology suppliers, processors, sensors, tools, algorithms, and so on, who are working together to raise awareness among product creators about what is now possible with vision technology and how to use that technology effectively to bring visual intelligence to all kinds of products, including products that are very constrained in cost, power consumption, and size. We do that through our website, through presentations like this, and through our own events. As Ori mentioned, our big event of the year is running tomorrow here, co-located with AWE. It's called the Embedded Vision Summit. And it's a full-day event entirely focused on practical technical education for product creators who want to understand how to bring visual intelligence to hardware and software to create new kinds of products. We've got some great keynote talks, including the technical lead from the Google self-driving car, Nathaniel Fairfield, will be here. The head of artificial intelligence at Facebook, Jan LeCun, will be here. 16 very high quality, practical, technical tutorials from experienced practitioners, and about 30 demos of some of the latest processors, algorithms, applications, tools, and so on from leading vision technology suppliers. Welcome you to find out more about the event, and if you're interested, to register to attend tomorrow at the website embeddedvisionsummit.com. So what we mean by embedded vision is practical systems that implement visual understanding, not only in big, expensive hardware, but in small, efficient, deployable systems as well. By bringing visual intelligence to our technology, we can make these products more aware of the world around them. And when they become more aware of the world around them, they can become more useful to us, easier to use, more capable, more responsive, more efficient. And the Embedded Vision Alliance is helping make this a reality by bringing practical know-how to product creators. I encourage you to visit our website, sign up for our newsletter, attend our events to make use of the great resources that these 40-odd companies are putting out for your use. On behalf of the member companies of the Embedded Vision Alliance, I want to thank you for your time. Thanks to AWE for having me. And if you'd like a copy of my slides and links to those many videos that I wish I had time to show you about cool vision-enabled products, please feel free to just send me an email using this email address. Thank you. Questions?
So do you see the future of embedded vision being with parallelized computation on general purpose GPU cores on processors, or with ASICs that
So that's a great question, which is could be a whole other hour-long presentation. In fact, I'll give a half-hour-long presentation on it tomorrow at the Embedded Vision Summit. But the short answer is there's a hierarchy. CPUs, GPUs, DSPs, FPGAs, many core processors, down to very specialized ASIC-type structures. The more parallel and the more specialized you go, the more operations per second per watt and operations per second per dollar you can get. But the more costly it is to deploy, to build that processor and then to program that processor. So in general, you go as far as you have to. And so for an automotive system, for a factory system, you're lucky. You can just run everything on a CPU, right? For some kind of industrial system, you might have to go to GPU or medical imaging product for a clinical setting, for example. For a car, maybe you have to go to a DSP. And for a wearable, maybe you have to go to an ASIC because you really have to get the absolute maximum efficiency. But it's going to cost you. It's going to cost you in the NRE, the engineering costs to build that custom hardware, and then the extra development cost to program that very, very specialized engine.
And what's the outlook like for generally applicable ASICs that, for instance, will run in the background with the main CPU off, do feature detection and trigger an interrupt the way a tap would on an accelerometer, except it's seen a possibly interesting feature?
Yeah, so it's a fantastic question. It's challenging in vision because of the variety of things we want to do with vision. One moment I want to recognize faces, the next moment lane markings in the roadway, then gestures, then I want to count people. So to put that into dedicated hardware is difficult. So I think where it's going to settle is for the applications that really need to push efficiency, they'll use highly, highly parallel and specialized, but still very programmable engines like you're going to hear about from Simon Morris of CogniView.
Thanks.
Sure.
Hi, Jeff. Thanks for your presentation. So I like the last question because that's, I think, what keeps you and I up at night as we design these systems. My question is, once this is available, whether it's fixed function or programmable, how do we get it easy for developers to figure out how to do computer vision stuff? I mean, computer vision stuff is for technically astute people to invent the capabilities that we're trying to do. How do we make this broader so that average programmers can figure out?
I think that's a fantastic question. I think AR is a place where we can see a kind of very nice case study of that happening through AR SDKs like Mateo and Vuforia, where they're abstracting away all the details. People can build visually intelligent applications using AR SDKs without knowing the difference between edge detection and contrast enhancement, or a Huff transform and optical flow. Those details are hidden below APIs that say things like, hey, tell me if this kind of an object appears in the field. Okay, now I've identified that object, please track it for me. So I think that's shining the light in how this is going to happen, and AR is possibly furthest along in terms of the domains where those SDKs are available and starting to be mature and quite powerful in their capabilities. Okay, I think I've used up my time. If you have more questions, I'm happy to try and answer them later.
Thank you, Jeff. That was fantastic.